Hi guys, you're watching Science Made Simple, only on TV16. Today, we're going to learn about CSTR dynamics. Let's check it out.
I'm an albatross. I'm an albatross.
Okay, so today we're going to talk about CSTRs. But before we proceed, let us see what CSTRs are all about. So let's take a look at what we have here on the whiteboard. First of all, CSTRs. CSTR basically stands for Continuous Stirred Tank Reactors. Okay, so what is it all about? Let's recap what we covered in our previous episodes, which is, if you remember, whenever we talk about chemical reactions in chemical plants, okay, so in chemical plants, reactions can be done either in batch or in continuous flow. So we have here batch or continuous. Okay, what's the difference between these two types of reactions? Batch is basically a one-shot reaction, meaning that there's no continuous feed in or out. One reaction happens in the tank, and once the reaction is over, we take the products and we take a whole new batch all over again. But for continuous flow, it is continuously run. So we have a continuous flow of feed and also an exit stream all the time going on. Okay, so for continuous flow, continuous reactions, we have two types of most commonly used reactors. First is PFR, which is plug flow reactor, and second is CSTR, and that's what we're going to cover today. Okay, continuous stirred tank reactor. So let's have a look at how does the CSTR look like. So a very simple schematic diagram will look like this. This is a tank. Okay, so as the name suggests, continuous stirred, we have a stirrer or an impeller, okay, inside the tank, and then we have a continuous flow flowing in and out of the tank. So go here and then out. The inlet stream, we call it as FA0, the inlet flow, and then we have FA as the exit stream. And the concentration of your reactor, which is A, is CA0 at the entrance, and it exits as CA. Okay, and this is your liquid. The thing about CSTR, whenever you want to use CSTRs, you have to make sure that one of your phases are liquids. So it can either be liquid-liquid, liquid-solid, or liquid gas. But liquid has to be there in order to use CSTRs. Okay, so let's take a look at the characteristics of CSTRs. First of all, CSTRs are done in steady-state condition, meaning that there is no accumulation done in the tank. Second of all, we have a continuous feed and exit, meaning that the flow in and also out of the tank is always going on, as compared to a batch reactor where there's no feed and there's no exit. Only reaction happens there in a single tank. And third of all is a uniform reaction. This is the most highlighted characteristic of the CSTR, which is different from the PFR, meaning that whenever you have an inlet going into the tank, you will immediately drop, becoming the same as the concentration inside the tank, and the concentration inside the tank is always the same as the exit concentration, okay? Which is not the same as PFRs. Okay, so next we take a look at what are the advantages of using CSTRs. So first of all, as it is a continuous reactor, means that we can produce in large scale because we have a continuous reaction going on as compared to a batch reactor, which is usually done in small scales. Second is temperature control. CSTRs are way easier to manage the temperature as compared to other types of reactors. It is also very simple to construct. As you can see, there's only a tank and an impeller, flow in and flow out. Okay. Number 4, low operating cost. And last but not least, it is very easy to clean as compared to other types of reactors. And also, when you have advantages, there's always going to be disadvantages. There's two main disadvantages about this type of reactor, which is, first of all, it has the lowest X. What's X? X is the conversion, meaning that if you have a product A, you want to convert it to B, the rate of conversion is the lowest per unit volume, meaning that if you want to reach a particular X, particular conversion rate, you will tend to you need a bigger size of reactor if you're using a CSTR. Okay. Second of all is bypassing may happen if poor agitation is used, meaning that if your impeller, is there something wrong with your impeller and the mixture is not properly mixed together, you will there will be bypassing. Bypassing meaning that, okay, let's take a look at the reactor again. When there's an inflow, there's a possibility that this particular molecule that enters straight away exits the tank without actually being reacted inside the tank if we have poor agitation happening. Okay, so before we go on to the next part of the video, let's take a look at some cool derivations that's related to CSTRs. Okay, check it out. Okay, so now let's take a look at some derivations related to CSTR, which we're going to conduct a mole balance equation for CSTRs. So how does it look like? Let's take a look on what I have to write on this paper. Alright, let's have a look. Okay, so for CSTR, the general mole balance equation. Okay, the general equation looks like in minus out plus generation equals to accumulation. Okay, so if you remember the diagram of our CSTR, it looks like this, right? Your tank, you have your impeller, your stirrer, and then you have an inflow of FA naught, the outflow is FA, right? So we take this into the equation, so it becomes FA naught minus FA plus generation becomes the integral of 0 to b of RA dV equals to D and A minus over dt. Alright, so let's separate the terms one by one. We go with this term first, the accumulation term. So first assumption is that we're saying that this is a steady state reaction, right? Steady state. So whenever we talk about steady state, it means that there's no change with time. So your D and A dt term will become equals to 0. Number one. Number two, for the rate of reaction, since this is a CSR, we're assuming that the rate of reaction taking place throughout the tank is the same, since the composition is uniform throughout the whole tank. So this term, so RA will become constant, so we can take it out of the integral. So when you integrate 0 to b for dV, you get V. So this term will become RA V. Alright, so your generation term becomes RA V. So we put these two values back into the equation. It becomes FA naught minus FA plus RA V equals to 0. Alright, so when you rearrange, you take it to the right hand side, it becomes negative RA V equals to FA naught minus FA. V as the subject, it becomes V equals to FA naught minus FA over negative RA. Alright, so this is your basically your equation for the volume of the CSR. Now let's take a look about the conversion. If you remember, conversion is equal to FA naught minus FA over FA naught. Okay, so you put rearrange the equation, bring it up here, it becomes FA naught x equals to FA naught minus FA. So you replace this term into your volume equation just now, it becomes V equals to FA naught x over negative RA. And this is your most commonly used equation to calculate the volume of a CSTR. Alright, so that is all the theory that you should know about the CSTRs. After this, we're going to have a look at the experimental procedures on how do you actually see the CSTR dynamics. So we're going to have a look at the lab with Dr. Haris and Dr. Alif. So let's check it out.
Hi, my name is Alif.
My name is Haris.
Today we're gonna do an experiment about CSTR dynamics. Let's go.
Okay, first of all, let's take a look at the apparatus setup.
The experiment consists of 3 CSTR reactors connected in series. As you can see inside of the reactor, we have conductivity sensor and temperature sensor.
This is the stereo system to control the stereo speed. This one is the main control panel. As you can see here, there are 3 readings of conductivity, and there are 2 switch of the pumps. This is the valves, all the valves that's connected from the feed tank and also the connected to the reactors.
This is the left time coil that we have to use in experiment in part C.
At the back of the apparatus setup, as you can see here, there are 2 feed tanks. Feed tank 1, which we need to fill up with the deionized water. The water will be from the water source and go through the deionizers and fill into the tank.
And this is feed tank 2 that we have to fill up with sodium chloride solution, and the solution we have to prepare it manually.
Centrifugal pump that we mentioned just now.
Waste tank that contain all the waste from the experiment.
Let's take a look at the software used to record the readings. The name of the software is Soltex. As you can see, Soltex CSTR in series.
The experiment consists of 3 parts, which is part A, part B, and part C. For part A, we have to investigate the step change input. Okay, for the first one, we have to fill up the feed tank T1 with the ionized water.
Okay, the second tank, the feed tank 2, we need to prepare 10 liters of 0.025 molar of sodium chloride into this tank.
Set the 3-way valve V3 towards the P1 position, and we have to switch on the main power.
Okay, then we need to open V5 and switch on pump P1 to initially fill up the reactors with the ionized water.
Next, we need to control the needle valve V4 to obtain the flow rate of 150 ml per minute.
We need to set the stereo system 1 to 3 to 200 RPM and continue pumping the ionized water into the reactors until the conductivity readings here will be at low and stable.
Next, we have to switch off the pump P1 and set the three-way valve V3 towards the position of pump 2 and switch on the pump 2. We go back to the software. We have to record the conductivity values. Click on the experiment A, and we have to set the suitable interval, which is 60 seconds, and click on auto record as simultaneous as we switch on the pump P2.
Okay, after we get all the conductivity readings are constant, then we need to switch off the pump P2 here, and to drain all the liquids we need to open the valve V3, V13, 12 and 11 here to drain all the liquids into the waste tank, where the procedures are basically the same with experiment A. But the difference is the tracer injection for experiment A and experiment B are different. In experiment A, we need to inject the tracer for continuously until the end of experiment. But for experiment B, the pulse input change, we need to inject the tracer for only about 2 minutes from pump P2.
And the second difference is, for the experiment A, we have to stop the experiment when we get the conductivity values to be constant. And for the part B, we have to stop the experiment when we got the conductivity value to be the same as the initial value for the conductivity. Okay, for the experiment C, which is the investigation on that time coil, basically the procedure is the same as experiment B, but the only difference is the setup of the valves. For this experiment, we only use one reactor here. So how to do that? We have to close valve V5, close, and we have to open valve 15 and close valve V10. Okay, basically we have to run the experiment until we get the conductivity value to be constant and record all the values. And we have to repeat this experiment by partially open valve V10 to let the solution flow through that time coil, and just record the conductivity values until you get the values to be constant.
Okay, now we are done with our experiment today.
Okay, to check our result, let's visit our analyst, Shada and Non.
Let's go. Hi guys, my name is Badmau. I will be speaking about the impulse inputs, and then
Hello, my name is JAN16 and I'm going to explain for the step input for this experiment.
here I will be speaking about the results about concentrations versus times in the CSTRs. So if you look at the graphs here, there are graphs for 3 reactors. Reactor 1, look here, reactor 2, reactor 3. So if you look at these graphs for reactor 1, it goes up and comes down like this. And then look at graph 2, then for reactor 3. So if you compare these 3 reactors, which has the highest concentration is reactor 2. You can see here reactor 2 has highest concentrations against time, and then followed by reactor 3, which has another higher concentration. Then comes also back to reactor 1. So reactor 1, we compare the concentrations. Reactor 1 is the which has least concentrations. And then we plot against the mean result times versus time. Still compare 3 reactors. One is reactor 1, which is the blue one, and then it's also reactor 3,
then reactor 2, then reactor 3. So if you look at recent times, you find that reactor 2 has the highest recent times, and that's why it has the highest concentrations. And this one is also reactor 1. If you compare them, reactor 1 has the least recent times. So here again is we did also the experiments about dead times, which was the dead time coil set parallel to the reactor series. So the results, look at the results here. The graph started from here, then goes up, then goes down. And the dead time here means that it is a dead time coil represents stagnation zones in non-ideal reactors. This is a zone whereby there is no reaction taking place. You can see here, look at the graph. It means when it comes at this time, the reaction goes up, then comes down. So this side, when it is going down, there is no reaction this side. And then the reaction again continues, goes up, and then comes down. So where the graph is going down is where there is no reaction taking place. So this is action of dead time zone. Thank you.
Based on the graph concentration versus time for step input, we can see that the reactor 1 has highest concentration for the first 40 minutes. However, after 15 minutes, the concentration of reactor 2 rose high up compared to the other two. This is due to the presence of many ions, result of proper mixing and continuous supply from reactor 1. The difference in concentration over time in these three reactors as account of adequate mixing and the time spent in each reactor. So that's why the reactor 1 has the lowest concentration, as it has less time spent and inadequate mixing in the reactor 1. Next, for the second graph, mean residence time of reactor 1, the blue color, it increased sharply, but after few minutes it dropped drastically up to 0 at 40 minutes. This is because the solution being passed on to the reactor 2 continuously. Same on the reactor 2, the orange color, it start increase and then reach its maximum height. After 10 minutes, it decreased as the time went up to the 52 minutes. Last, for the reactor 3, the curve here rose up made almost constant curve, as it doesn't drop this drastically like previous reactor, as the content was not flow to the other reactor.
Okay, my name is Muhammad. I'll be speaking here about concentration versus time for pulse inputs. Pulse inputs is when you put the tracer only once, and then we plot it for three reactors. Reactor 1, which is the blue one, goes like this one here, and then reactor 2, which is the brown one, and then the gray one, also reactor 2. So if you compare these three reactors, the concentration for reactor 2 is the highest one, then followed by reactor 3. Reactor 1 has the least highest concentrations. This is because in reactor 2, there is the one which comes from the reactor 1 gets mixed properly in reactor 2, and then there is breakdown of the ions, which leads to highest concentration in reactor 2. Next will be residence times. We compare the residence time for three reactors. You see that the solution spent a long time in reactor 2. This is reactor 2, so that means solution spent much time in reactor 2, and then also spend a lot of time in reactor 3. Then reactor 1 is the least one. The reason for this is that reactor 1, as soon as it goes to reactor 1, it is passed on to reactor 2. Then water mixing goes on again, and then reactor 3. The next one will be dead time. Dead time was set up parallel to the reactor series. So when you look at the dead time is where it represents the stagnation points in non-ideal reactors. And you see the curves here. The curves set it and goes up, and then slope down, decreases down, then also increases up, then decreases down here. So the decrease here is whereby there is production response in the reactor, and this side there's no response, that's why it is going down. So this point we call it the dead time points. Then it goes again, after passing the dead coil, there's also a reaction taking place in the reactor, and then it comes to the dead time also. So all these dead times, this part and then also this part which is going down here, represents the stagnation points in the non-ideal reactor. Thank you. I'll pass on to my friend Haida.
Okay, we have done for the result and discussion part before. Now let's proceed to the error and recommendation. From the observation, we found out that there are several errors occur in the experiment. The first one is the difficulty in flushing out the leftover chemical in the reactor. So we recommend that to have a vacuum sucker in each of the reactors so that the chemical can easily flush out and there's no chemical left in the reactor. Now I pass to the Dengot to the next point.
Okay, thank you, Ada. The second error was the leakage of feeds from feed tanks. So the feed tanks, there's some piping, when you just don't correct the pipes very well, then the leakage of the feeds, which way after the results. So that what can be done is the piping on the feed tank should be repaired properly, should be connected, then the joints if there is any leakage, then you have to connect it very well to prevent the leakage of the feeds from the tank to make the good results. So that's what was about runtime error. So the computer, runtime error here, the reactor and the computers, data should be calibrated. Calibration needs to be calibrated to get the good results, so that the drops doesn't go in the battery. Those are the things that we have got, the errors and recommendations. Thank you. Okay, that's all from us. Now we pass it on to pass back to Alif and Hayes to conclude our experiments. Hi guys, my name is.
Hi, it's us again, Haris.
And me, Alif. Today we're going to conclude about CSTR dynamics experiment. Okay, first, the step process injection is when we inject the traces inside the reactor continuously throughout the experiment.
Okay, for the second point is pass input change. The traces will be injected into the reactors for about 2 minutes only.
Okay, RTD is residence time distribution. Means that is how long the reactant spent in the reactor to complete the reaction.
Alright, and last but not least, reactor based on our experiment, second reactor is the highest concentration, also have the highest RTD compared to other reactors.
Okay, thank you.
Thank you.
So guys, basically that's the end of our episode this week. I hope you guys have a very good understanding of what CSTR dynamics is all about. Stay tuned for more episodes of Science Made Simple only on CDB60. Thanks for watching and have a nice day. Bye.